Dublin Institute of Technology, and I did my PhD here in UCD. And in 2013, I was awarded the European award in order to study and develop self-healing asphalt pavements. And that's actually the title of my presentation today, is Self-Healing Asphalt for Road Pavements, and it's funded by Marie Curie Fellowship, and it's done in TU Delft under supervision of Professor Eric Schlangen. So just to give you an overview of today's presentation, I will talk to you what motivated me to do this work. I will introduce you to technology available today for self-healing technology for asphalt pavements. Then I will introduce you what we're going to do in the future. I will talk to you a little bit about self-healing concrete. It's another material that we are looking into. And then I'll conclude and finish the presentation. So what motivated me? Well, and what motivated the EU to fund my research is actually importance of its road network. But they believe that in EU that road network is very important for the economic growth and social cohesion. And now with the increase of European Union enlargement, we do need that road network to stay in use non-stop. And recently, European Laboratory Organization launched the Forever Open Road. So they don't want any maintenance or construction on the road as it happens. Today, in the world, we have about 16.3 million kilometers of the road, and EU has 5 million kilometers. It's the largest road network in the world. And to maintain that road network, EU spends, countries generally spend about 20 billion euros. Ireland spends about 50 million. And from this, we can see that it's actually very important for us to start looking into novel technologies for the prevention of road failures. So one of the new technologies is self-healing technology. And today we have binder rejuvenation, we have microcapsules or fibers, and we also have induction heating technology, which it's done using the steel fibers which are embedded in the asphalt pavement. I will talk about it in a minute. So I will start with rejuvenation. Rejuvenator is material which is inserted in asphalt pavements as a healing agent, and its primary purpose is to diffuse into the aged bitumen and restore its properties. In other words, it actually softens the bitumen and allows it to flow, close the cracks, and repair the damage. The different types, we can have real rejuvenators. They're industrially produced. They completely repair material, and then we can use different types of binder, high pen binder, or organic oil such as vegetable oil, cooking oil that we have at home, or waste cooking oil itself. Difference between these materials is that waste cooking oil just softens the material but doesn't really reinstate its lost properties, such as these maltines and saturants, where the industrially prepared material will do that. So today, industry actually uses these rejuvenators. They simply pour over the surface of the asphalt and allow it to drain into the depth. However, it can only penetrate maybe top 20 millimeters. It doesn't go any further. So any cracks that are occurring at the bottom of the asphalt layers, they will not be closed, and or damage won't be repaired. So the solution is to encapsulate these rejuvenators and embed them during the construction process of the road pavements. And how does it work? Well, it's very simple. So once the capsules are embedded in the pavement, they stay there till crack starts propagating. When cracks propagates, energy at the tip of the crack will encounter the capsule, break it, and then release the rejuvenator. The rejuvenator will then diffuse into binder, soften it, allow it to flow, and close the crack. It's a very simple process. The materials for encapsulation, we have different types of capsules that we're studying. First is porous sand. This is simple sand that we can buy in our department stores. This is a cat sand. It's a porous, absorbs the liquid, so we saturate it with the rejuvenator, and then we apply coating, epoxy coating, And then we have something like this, we have a core here and a shell around it. And then when we break it, we can see that there is an aggregate in the asphalt material full of rejuvenator. When this breaks, it will release the rejuvenator and repair the damage. Another method is using the methanol capsules. I'm not trying to pronounce the rest of the chemical use, but it's basically polymeric capsule which is embedded in asphalt pavement and encapsulate the rejuvenator. Principle is the same. Again, when capsule is broken, rejuvenator released into the crack. Disadvantage of this approach is that these capsules are very small, so we need large volume with the capsules. And this material, formaldehyde, it's a dangerous material for the human health. So large amounts of this material in the road could pose a threat for human health. So if we have a leaching, it can leach into the waterbed. And final solution is to use alginate. Alginate is a product from algae. It's organic. It's readily available. It's used into the encapsulation of the medicine, and so it's it's not doesn't pose any damage to human health. And this is something that I'm working on. And we can encapsulate it in the form of microcapsules or microfibers. And these fibers are looking as shown here in the image. And the reason why we don't have full hollow fibers is to allow it for the crack to hit one capsule, so we can heal multiple cracks. If you have only one full hollow fiber, then we can heal only one crack at a time. So that's the advantage of these compartmented fibers. So advantage of encapsulation is that the rejuvenator can heal bitumen damage. There are various microcapsule techniques which effectively encapsulate the rejuvenator. Microcapsule fibers can survive the production process. Fibers can increase the strength of the material up to 36%, and rejuvenator shows potential for self-healing of asphalt pavements. Disadvantages: it has a very limited healing capacity. It can only heal micro cracks. It can't heal the large damage. So if you can imagine, if you have a large crack going through the surface, it will not heal it. It will only be effective at the very outset of the crack propagation. Now, second stage is induction heating. This is more efficient process. In this process, we insert the steel fibers, simple fibers that we can find in any kitchen, housing kitchen. Those steel wool that we can clean pans in the kitchen. So we insert that into the asphalt pavement, and then when crack occurs, we induce induction heating. This heating heats the steel fibers which are embedded in asphalt pavement, melts the bitumen, and closes the crack and repairs the damage. This is how it actually looks, distribution of the steel fibers in the mix itself. But we also can use graphite. Only advantage of steel fibers is that they have a better resistivity, so it can conduct the electrical energy better, and also it can introduce the higher strength of the material, so increase the strength of the material. So here's a simple test when we have a 2-point bend specimen, and we simply cool it down to 20 degrees, broke it, then heat it for 2 minutes, and then it was repaired. And process was repaired 6 times, and at 6 times we lost about 70%, and then after that about 50%. So we can repair the damage 6 times before we can call it its full repair of the pavement needs to be done. Similar experience was when we subjected the test specimens to fatigue loading. This is constant loading, repetitive loading, and we could actually bring it down to the failure and then heal it again about 5 times before it's fully damaged. Dutch authorities are very happy with this, and they allow us to actually bring this technology from lab to the site. So we have about 400 meters length of test site on the Dutch highway A58, and was laid down in 2010. Test period will last about 10 years. And the first repair was done in 2014. We managed to develop the actual induction machine for on-site repair damage, and we can see it's still under prototype process. But it works, and the road is still there, working really well. So advantage is that this fast repair time, 2 to 3 minutes. Maintenance can be repeated many times. Disadvantage still is very expensive. And healing efficiency decreases with number of the healing. So we're introducing the aging in the process. So our solution is to combine two technologies together. So first, induction heating will be used for actual repair of the damage, and rejuvenator will be used to actually just freshen up the bitumen. Now, just to give you some insight into what we are working now on as well, it's this super hyper road. So we are combining with our electrical engineering department, and we are developing a road which we allow the recharging batteries in the electric vehicles continuously as they're traveling. And that will be inserted in the middle of the road, and then these two self-healing asphalt pavements where there will be tracks for the wheels that travel over will have a self-healing material in it. The induction coils will be actually embedded at the bottom of the asphalt pavement, and technology already exists, and it's still in the lab process. And we actually can link with the solar roads, which are already used on bike lanes in Netherlands. So we are aiming to have this concept on the road by 2030. Just to give you quick insights in self-healing concrete, which probably is more in line with this summit. So one of the technologies that we're using, it's a healing agent use bacteria. Process is similar. We encapsulate bacteria with some food in alginate, and we embed this in the concrete during the construction. During before cracking, bacteria is in a dormant state, just sleeps. And when cracks occurs in concrete, water penetrates into the crack, then reduces the acidity of the concrete. Then bacteria wakes up and starts eating and producing calcite. Calcite closes cracks, and the bacteria then, once crack is closed, acidity increases, bacteria goes back to sleep. As long as there is a food, this process can be repeated over and over again. Now here we have example of a test sample with bacteria microcapsules, and we can see here two samples, one with capsules, one without. And we can see after healing that actually the sample without the bacteria had no repair, and with bacteria repaired the crack completely. So it's very effective. Our test site we have as well in Netherlands, this pavilion in Breda. It has a concrete roof. Originally this is supposed to be produced with this self-healing concrete. However, the architect and owner decided not to go that direction, but after a while we actually start getting cracks in material, then they call us back to find a solution. So we produced a material solution with these bacteria capsules in form of liquid. So you can simply spray on the surface of the concrete, and it's also effective, and you can see the cracks are closed. Similar technology is used now in car parks, where we have large cracks in the car parks. So this material is commercially available. It's produced by the company Basilix. It's owned by its inventor Henk Jonkers. He was awarded a European Inventor Award for this product. And you can find more information on the site. So in conclusion, self-healing asphalt concrete work. Further development of self-healing roads means less maintenance, fewer traffic jams, lower environmental impact, and in general, long-term, we have cheaper roads. However, future progress of self-healing materials, it does not only rely on civil engineers, but will actually be a product of the combined effort from civil engineers, chemistry, biology, electrical engineering, mechanical, and so on. So with this, I will finish my presentation. Thank you very much, and enjoy.